This last example, we were looking at a stereogenic center here, and we wanted to determine if it was S or R stereoisomer, and we first need to identify priority. So I have shown you this drawing out method where we're going to swap these. I've prioritized the different groups here. The heaviest molecular weight unit here is the chlorine, followed by the hydroxide, the oxygen. Here we have a carbon that's attached to an oxygen, so that gets the next priority, and then we have a carbon just attached to a carbon. So we've prioritized these here, and numbered them based on the priority, first, second, third, and fourth priority. And then I've drawn out the swapping of just the numbers. So I'm not moving any of the things, and again, that's going to be really hard with a ring structure attached. So it's going to be really hard to move that ring around or swap it around and make this enantiomers. Remember, we're just moving the numbers. So to get that high priority out and put the low priority down, rather than trying to redraw this in that way, I'm just moving the numbers from 1 to 4 and swapping those out. So that's the first swap. And then to get back to my original compound, I have to turn this enantiomer into its enantiomer, which gets me back to the original. Again, I'm not redrawing the whole structure. I'm just going to swap the numbers out. So I swapped 2 and 3, and now I can do my tracing. I will go from 1 to 2, skip over 4 to 3. So we can see that this is clockwise, and this is going to be in the R conformation. Here we can again use that numbering system to swap, and trace the arc. And we're going to make sure that with these lower priority hydrogens right now are not in the back. Here it is though, for example, but some of them they are, some of them they're not. You're going to want to get that into the back or back of the image so that you can do that tracing and get the proper name for that. Take a second to try these out. If you have questions or problems, let me know. You should get the answer of SRS, SR, but make sure that you can do those. Make sure that that works. And if you're having problems with that, come and see me or try to figure out what's going on. Remember, you have to prioritize them, so check the priority. Then you swap them once and get that low priority in the back, and then you have to swap the other set to get those values, to get the structure back to the original enantiomer. And that should help you determine S versus R. Remember, you skip over that low priority in the back. Now that we've looked at some different kind of structures that maybe they're rings or they're more complicated, I do want to introduce you to another commonly used mechanism for organizing chemical structures, and specifically for looking at sugars or different carbohydrate compounds. So Fisher projections that are shown here are a stylized way of conveying the three-dimensional shape of, in 2 dimensions, and it's very common in biochemistry. The convention is where there's this cross shape that's formed, and you can kind of see where these are kind of going back into the screen and the wedges are coming out at you. So you can see that we have those vertical and horizontal arms that are coming out or going back. What you'll also notice is that there are perhaps multiple different types of chiral centers in the middle of these bonds. And for example, let's look here. We have a hydrogen attached, and the carbon is right here in the middle. We have a hydrogen, CHO group, an OH group, and a CH2OH group. So that's attached to 4 different unique things, and this is a chiral center. Here is the mirror image. It's the enantiomer of the compound. So we have different things that, these are the Fisher projections, but a lot of times they're not actually drawn out with these dashes and wedges. They're just drawn out with lines because it's easier and quicker to 2-dimensionally just draw 2 crosses rather than try to dash and wedge these. Here's another example of the similar kind of idea, but it has actually 2 chiral centers rather than just one over here. And you can see it's drawn with these multiple crosses in this structure. But these are showing us the same thing. This means that we have to organize this a little differently when we're looking at identifying the chiral centers and determining and naming them as R versus S. So for Fisher projections, the rules are still the same. We want to get the priority and then we swap, and trace them. But now what we want to do is you want to get the low priority must be on the bottom when you're doing the arc tracing. So it's usually not, however, it's usually not on the bottom, because a lot of times, and especially when these are used for carbohydrates have a lot of hydroxide functional groups, alcohol functional groups, and those are going to be coming off to the side, typically when these are drawn. So the high priority, as in this example shows, is that alcohol functional group is typically going to be on the right, and then usually the hydrogen is on the other side of that high priority, but we need to get that to the bottom. So here's an example of how we do this. We would number the priorities as normal, and then we'd swap the 4 and 3 out to get the 4 on the bottom, and then we have to swap again to get the enantiomer. So I just swapped the other 2 that we didn't swap. So that now we would go from 1 to 2 to 3, and we can see that's clockwise, and that's going to be an R designation for the chiral center. If we're looking at D-glucose or L-glucose, so here we have D-glucose has 1, 2, 3, 4 different chiral centers. L-glucose is the same thing. It's just the inverse structure of it. And you can see that we have RSRR, so RSRR, and you could determine that the same method we used. We identify priority, get the low priority on the bottom, and then do that arc tracing, and it should give you RSRR. This is D-glucose versus L-glucose. Remember, these are naming conventions. SRSS, that's to name something, even if we don't have the how that interacts with light. These D and L designations, those are telling us that glucose turns the light, polarized light, to the right. L-glucose tells us that it turns the polarized light to the left. And so these designators are kind of the same idea, but they're actually the experimental values are determining that. Here are a lot of different types of carbohydrates. You have D-ribose, that maybe sounds familiar. Ribonucleic acid, it's kind of backbone for DNA. Arabinose, xylose, multiple different D types. These, you'll notice a lot of them are on the right side. However, D-lysose, that one has more on the left side. So, but it still bends light or turns light to the right side. So it's not always the same. R and D, S and L. Those are not necessarily the same thing. So take a second here. Assign the stereochemistry for L-lysose for each of those three different stereocenters, and let me know if you have any questions about that. Okay, so again, assign the stereochemistry for these 2 chiral centers. Pause here, and we'll start after you have a chance to work on that. So the name for these are, we have the butane 2,3-diol, and that's the base name, and then the one on the left is SS, and the one on the right is RR. So it's not really easy to just say, oh, okay, well, this one's going to the right, so that's R, and this one's going to the left, so it's S. You can see here, after you've named those, that's not necessarily the case. So you're going to really want to assign those priorities every time that you see these Fisher projections based on that mechanism I showed you in the last few slides. Not that you're necessarily going to want to or need to manipulate Fisher projections, but when you do, you can flip them around. You can do 180-degree spins. For example, that CO2, we can spin to the bottom. The hydroxides, we can rotate to the other side. We can flip the whole entire thing, but we can't rotate it by 90 degrees. We can't just say, okay, I'm going to rotate the hydroxide, down on the bottom, and we're going to make them sideways that way. It doesn't work that way because, again, that changes the orientation and where these things are organized. So that wouldn't be an appropriate way to do that. if I do this 180 degrees and I rotate these out, we'll still get the same type of readout for this second R group is going to, the second chiral center is going to be R, this third is going to be S, and so it doesn't matter which way we do it, it'll still have the same. If we rotate it 90 degrees, meaning that we would flip just one of these around, then we would change that conformation and it's not going to be the same anymore. Here's an important vocab word that I'd like you to know. It's this mesocompound, and mesocompounds are when we have structures that have a superimposable mirror image that you can draw down the middle of one different molecules. So they're basically optically inactive. So when we talked about, even though they have chiral centers, what is going to happen is that you have this alpha, that rotation of light is actually going to be 0 because one of the centers is going to rotate it one way and the other center is going to rotate the light the opposite direction, and it's going to basically cancel each other out. So here you can see, if I draw this down, this line down the middle here, they're mirror images of each other along that line. And so those will cancel, that light turning will cancel each other out. Here, these are not mesocompounds. We have different compounds. These are diastereomers, which means there are two stereogenic centers, but these are not mirror images of each other. So when we look at this rotation of light, it does have a value here. This alpha value is positive or minus. It's not zeroed out. So these compounds will rotate light. Important vocab words to know so that when we're talking about these things, we can have the same language and discussion. Here is an example of, these are enantiomers. And so the enantiomers here, there are mirror images of each other. So these are enantiomers. Each of these enantiomers are also mesocompounds because we could draw a line between the two spaces and they would be mirror images. Or if we fold this piece of paper in half, they'd line up and match each other. So these are enantiomers of each other, and each of these is a mesocompound. On the right side here, if we draw a line down the middle here, these are diastereomers, so they're non-superimposable, non-mirror images. So they have two or more chiral centers, but one center is different than the other. So this one center is the same, this center is different. So these are diastereomers. So some vocabulary to know and understand. Here are just kind of a chart, organizational chart that kind of goes through some of the differences in, if we're looking at enantiomers versus diastereomers, to help you look at and see those differences maybe a little different, not on a Fisher projection level. So if we have two different chiral centers, they're both R designated. And if we go over here, they could go both to S designated. So we'll see that these are mirror images of each other. These are enantiomers of each other. Now, if we just change one of these, for example, this red chiral center turns from an S to an R, then what happens is these become diastereomers of each other. So they're non-mirror images of each other because we have one is the same, but then this other one is different. Now we also can change these to, if we look at these over here, we can make other mirror images, and that these are going to be enantiomers, and then these are diastereomers from the starting point. So some just ways of looking at this and understanding what enantiomer versus diastereomer means. The vocab in this chapter is important, so it's helpful to understand these different terms. And if you have something that's optically active, it contains a chiral center. It is a chiral compound. If it's inactive optically, it either it's either achiral, so there's no stereogenic center. It's going to be a mesocompound, which means that itself, you can fold on itself and it has a mirror image of itself within itself. or it's a racemic mixture and it maybe has an even mixture of the enantiomers. So again, just kind of an overview of some of the terms that you should know regarding stereochemistry. So here's an interesting thing to try out. I would like you to see if you can, first you'd identify the chiral center. And we've done these before, so you should be able to look back at those and determine R versus S. But I'd like you to try to convert these to Fisher projections. So for this first example here, let's say this is your eyeball. You're going to kind of look at it from this direction. And I'm looking down here, and this is the chiral center. So on the left side of the Fisher projection, I would have this carbon here that's on that dash line, and on the right I'm going to have the NH2. So if I'm drawing this out, it should look something like this. On the left side is my carbon, and H2 on the right. Up on top is a carbon that's here, and that's attached to this carboxylic acid functional group. And then down below on the bottom is the H, so that's in the background. So now we can look at this. We could recognize high priority is this nitrogen. The second priority is that carboxylic acid attached carbon. Third priority is here. Fourth priority is here. We want 4 on the bottom anyway, so we can trace it. And then we know that is counterclockwise, so this is going to be S designation. So try that with these other compounds. And you might have to kind of look from the left side, like this one, or maybe on this other one over here, you might want to look from this side, this angle, so that you can see where that would line up for your Fisher projection. So it kind of depends on where that dash or wedge is pointing to the left side or the right side. But try that out, and I'll give you pause here and work on that. Okay, so we'll continue. I'm going to show you what you should have come up with in terms of the Fisher projections over here. And this would be, again, you're not necessarily going to need to do this, but sometimes just practicing this helps you work with this spatial understanding of these things. And I'm going to highlight the different chiral centers here. And you should be able to identify the priority again, just like we've been doing before. We want to get the high priority on the bottom. So in these first 3 on the top, the low priority, sorry, on the bottom, the low priority is on the bottom already. Some of these other ones, this one is not, and this one is also not. So you'd want to change those around. So, but you should have gotten those in terms of being able to identify. We determined this was S already, and here we should get R and an S, and then we would have an S and an R, I believe. So that's what you should have gotten. If you did not, maybe check your priority, check to make sure that you got the low priority on the bottom. Stereochemistry is really an important idea in organic chemistry because really we're mostly only interested in one type of stereochemistry, especially if we are synthesizing something for some type of biological use. So when you're synthesizing something, sometimes you'll get the meso mixture. You'll get the mixture of 2 different compounds. You might have chiral products from achiral reagents or chiral products from chiral reagents. And here's just an example of one where we'd have L-methamphetamine, which is a nasal decongestant over the counter. It's not psychoactive, but the enantiomer of it, this mirror image version of it, is what most people refer to as meth. So this is a controlled substance. It has psychoactive characteristics, and it's just based on this little change of where that methyl group is coming off of this chiral center here. So what do chemists do about this? Well, one of the things that can be done is when these meso compounds are where they have structures that are superimposable mirror images and they are optically inactive. And again, just going through that vocab. But you notice the enantiomers have an alpha value and the meso compounds don't. Also notice the melting points are different, and I didn't mention that before, but these things have different physical properties as well as chemical properties, and they're different, and they can be separated because of that differently. So you could identify them on thin layer chromatography if you just wanted to identify them. You could separate them out through chromatography techniques because they have those different characteristics. We'd be able to pull those out and separate those from each other. We haven't necessarily gone through these types of reactions yet, but if we have HBr, what you'll notice is there'll be a partial positive and a partial negative here, and this double bond, the electrons in this double bond will tend to be interested in interacting with partial positively charged compounds. So we go through this intermediate here where we have that can form a positive charge on one of the carbons, because we would have that hydrogen attaching here. Remember, we already had two attached, and we have one here as well. So we'd have this hydrogen here, and then we'd have 3 on the end, and it would leave us with this positive charge here. We'd also be left with a bromine that'd be negatively charged, and we could then bond there. However, it could come from one side or the other. It could attach at either end, and it could give us a bromine that came out at us or a bromine that went back in. So this is common with addition reactions, and you're going to have an equal chance of reacting on either side of that positive charge. So usually this ends up as a racemic mixture, 50-50 mixture of both of these different enantiomers here. So as we start looking at different types of chemical reactions, we'll be wanting to look at this, and it can help us understand that mechanism that's actually happening, that we know this goes through this carbocation intermediate, because it doesn't all happen all at one time. If it happened all at once, we'd always have it coming from one way or the other. But since we have this intermediate, we have an idea that this is happening in multiple step process. If we have the same type of chemical reaction where we have a diastereomer, so we already have another stereogenic center here, and we're going to generate a second stereogenic center that's going to be on this other carbon. So the same type of chemical reaction I just showed you, but we can generate on one side or on the other. So here we'll generate diastereomers, and we'll have that will have different chemical properties and allow us to separate and prepare these and prep these differently. So here's just a starting point. You might have different enantiomers, R versus S. If you have a chiral reagent that we know is separated and purified out, then you would have unique diastereomers. That would be R and S or S and S. And then now these new products that are diastereomers can be easily separated from each other. And this works best when those resolving agents are easy to then take back off and remove, so that you can get back to your initial compound. I just want to go over a resolution scheme for it with you, and this is again just looking at in the future when we're looking at synthesizing things that might have be a mixture that's inseparable because they have very similar structures. We have a compound A that has one version of it's a stereogenic center, and we have a chiral reagent that we're going to be able to interact it with. So then we're able to generate diastereomers. So if we have with this would be S or R designation, and we would join them. And so putting these together, now we have diastereomers that are going to have different melting points, different chemical characteristics, as opposed to here where they would have similar characteristics. Now we separate and purify them. So we would want to just get, one group of them separated out, and we would distinguish them from the other group. And then we could if we can resolve this, we eliminate that chiral reagent, we could recycle it and use it again, and then we would generate our single enantiomer that's been purified. So these can be separated by chromatography, but it's generally impractical on a really large scale. If these things can be crystallized, that usually works the best. It's the fastest and quicker, easier option if we can crystallize these things out to separate them. rather than just A's and B's and pluses and minuses, I just wanted to show you an example of phenylethylamine. And we have this S and R version of phenylethylamine that we wouldn't normally be able to distinguish or purify out with each other. Tartaric acid's relatively cheap, about 16 pounds per kilogram, I guess. So that's probably about $20 a kilogram. And we could then interact them with each other. And these will form crystals. So this version, the S version with the tartaric acid, will crystallize out. This will remain in solution. So we'll collect the crystals. We'll be able to then dissolve the crystals with hydrochloric acid. And then we would extract this phenylethylamine within an ether layer. And then we'd be able to isolate that S versus R enantiomer from each other, and we'd purify that out. So just an example of that process for resolution of different compounds.